The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Ladies and gentlemen, welcome to lecture number 8. In this lecture, I would like to discuss with you the numerical integration and some modeling considerations. You might recall that in the isoparametric formulation that we discussed in the earlier lectures, we use numerical integration. And this is an important fact, and I want to discuss with you in this lecture the Newton-Cotes formulas that we're using, and in particular the Gauss integration, the Gauss numerical integration that we're using in finite element analysis. There are various considerations. First of all, I'd like to present to you a little bit of the theory that is being used, and then particularly, however, I also like to present to you some practical considerations. And finally, together with these aspects, I would like to also present to you some considerations regarding the choice of elements and, of course, regarding the choice of the order of numerical integration that has to be used in the finite element formulation. Well, just to refresh your memory, on this view graph, I put together once the various matrices that we have to evaluate. Here we have the stiffness matrix, which of course is obtained by the integral of B transpose CB, being B is the strain displacement transformation matrix, C is the stress-strain law. Of course, this B matrix is a function of x and y in the physical space, but if we use isoparametric interpolation in two-dimensional analysis, this B matrix will be a function of R and S, as we discussed earlier. The M matrix is given here, the RB load vector is given here, the RS load vector is given here, and the initial stress load vector is given here. We derived all of these quantities in an earlier lecture, and all I like to now discuss with you is how do we evaluate these quantities using numerical integration. In isoparametric finite element analysis, I mentioned already, the displacement transformation matrix is a function of R and S and T. The strain displacement interpolation matrix is also a function of R, S, and T in three-dimensional analysis. Of course, in one- or two-dimensional analysis, we only talk about R and S respectively. Remember, please, that R, S, and T vary from -1 to +1, and that we therefore need the volume transformation here, dV being the determinant of J, where J is the Jacobian transformation between the x and y and R and S axes, or x, y, and z, and R, S, and T axes. And, of course, dr, ds, dt are the respective differentials that have to be used here, too. We discussed that earlier. And just to refresh your memory again, what we came up with is that the stiffness matrix K is given in terms, for two-dimensional analysis, is given in terms of B transpose CB times determinant of J, dr, ds, and we are integrating from -1 to +1. The mass matrix is given as shown here, where H is, of course, once again, the displacement transformation matrix. Rho is the mass density. Just a preliminary thought, please recognize that B involves derivatives of displacements. We have here derivatives of displacements. Here we have the actual displacements. So the product of B transpose B will in general be of lower order than the product of H transpose H. Therefore, when we talk about numerical integration, we will find that to evaluate the M matrix exactly, we will have to use a higher order integration than in an exact evaluation of the stiffness matrix. I will refer to that again later. We also mentioned already that in the numerical integration, the basic process is that we are evaluating the function Fij as shown here at particular points ij, denoted by ij, and the alpha ij are weight coefficients. Therefore, what we do is, once again, is to evaluate this product at a particular point within the element, multiply that product by a weight coefficient, and then do the same for a certain selected number of points and sum all these evaluations up, as shown in this equation. Now, what this means, of course, is that we will have to use specific points, and I have to discuss with you what points we are using, and how many points is another question that we have to also discuss. Well, in 2-point integration, 2-by-2 integration, in isoparametric finite element analysis, we would use 4 points altogether. 2-by-2 means 2 points this direction and 2 points that direction. In 3-dimensional analysis, we would of course talk about 2-by-2-by-2. We would have another 2 points in this direction, in the t direction. These points in Gauss integration are given by these values here. In other words, point 4, for example, would have the values r equals plus 0.577 and s equal to plus 0.577. Point 1 would have the same values but both negative. These values here are the Gauss values, and I will discuss briefly with you a little later how these have been obtained. Of course, Gauss derived them for us some 100 years ago, and we are now simply using them. In 3-by-3 integration, we talk about 9 integration points altogether. Once again, 3 integration points, layers, so to say, in this direction and into that direction. If we use 3-point integration in 3-dimensional analysis, we would have altogether 27 integration points, because each of these layers, of course, applies then 3 times, and because we also have 3 layers into the t direction, and therefore altogether 9-by-3 being 27 integration points. The basic process of numerical integration is that if we want to integrate a function, and I've shown here an actual function, this heavy line is the actual function f. If we want to integrate that actual function with respect to x here, what we do is we are putting an interpolating polynomial down as an approximation to that function. Now, if we want to integrate this function from a to b, the simplest interpolating polynomial would be to put a straight line from this point to that point. And then the area under the straight line is assumed to be approximately, or at least really sufficiently close to the area under the actual function f. So what we are doing then is we are replacing the integral of the actual function f over this interval by the integral of the interpolating polynomial over that integral. If we do that with just 2 points, and the 2 points are these two, we will derive the trapezoidal rule. If we use 3 points, and I have here a view graph that shows how we would use 3 points, 1 point here, 2nd point there, and now we have also a 3rd point there, then we would obtain the Simpsons rule. Once again, instead of integrating the actual function f, which is shown by this line here, we are in fact integrating the area under this red line. This is a little weak. Now there it comes. We are integrating the area under the red line. In other words, the assumption is then that this area is close enough to the area under the blue line. And what we need to do is to evaluate, of course, the actual function f at these 3 points. And we will have to somehow develop certain constants, the alpha ij's that I talked about earlier, that multiply this function f in order to evaluate the area, the red area here, accurately. Well, if we do that, in other words, if we integrate the red area using these three function points, then we obtain the Simpsons rule, and this is just one rule of the more general Newton-Cotes integration. In the Newton-Cotes integration, we use equally spaced sampling points. In other words, if we want to integrate from A to B, the simplest way of proceeding is to use a sampling point here and a sampling point there. And then, of course, as I pointed out earlier, we are putting really a straight line down, and we are assuming that the area under this straight line is equal to the area under the actual function f that might be looking like that. Well, that is the trapezoidal rule, and the Newton-Cotes integration with n equal to 1, in other words with two constants here, is equal to this trapezoidal rule. What we are saying is that the area from A to B, now I used here r, this is the r-axis, say, from A to B, this is the actual integration, is replaced by the summation of the value at this point, the f0 value, the f1 value, and each of these values is multiplied by a certain constant. So in this particular case, for the trapezoidal rules that I'm talking about, the right-hand side looks as follows. B minus A, that is this length here, times two values. The C0, 1, n is equal to 1 in this particular case, times F0, plus C1, C1, 1 times F1. And of course then, plus an error, R, in this particular case, n once again is equal to 1 plus R1. This error, of course, is assumed to be very small in the analysis, and we will actually neglect it. So once again, what we are saying is that we can replace the integration of f of r dr from A to B via this summation here. Notice that b minus a times that constant, that is our alpha 1 that I referred to earlier, and b minus a times that constant would be another alpha value. And of course, these alpha values here multiply the actual function values at this station and at that station. Well, in the Simpson rule, n is equal to 2. B minus a is still there, but now we are talking about C0, 2 times F0 plus C1, 2 times F1 plus C2, 2 times F2, and of course an error R2 there. Well, the constants C01, C11, and so on, the constant Cin, have been evaluated for us, and they are tabulated in this table here. Notice that for the trapezoidal rule, we have the simple constants 1/2, 1/2. The error here is shown here, 10 to the minus 1 times the second derivative of f. So if the second derivative of the actual function is 0, well, then our integration is exact. Of course, what that then means is that our function is indeed a straight line, because only then the second derivative is 0. So our integration is exact when we integrate a straight line. Well, if you look at our earlier graph here, surely if our actual red line is a straight line between this point and that point, then our integration using the trapezoidal rule must be exact. And that is verified by looking at the error bound given in this table. The Simpsons rule has constants 1, 6, 4, 6, 1, 6. N is equal to 2 in this particular case, as I mentioned earlier. The error here is now given the fourth derivative. and so on. Here we have intervals 1 to 6. In practice, however, we would only use the trapezoidal rule, the Simpson rule, and we might then still use this rule here. Notice that the error of this rule here is of the same order as the error of this rule involving 5 points. So the 4-point integration rule, of course, is preferable when you compare it to the 5-point integration rule. The other important point is that if we use the Newton-Cotes formulae, we are really always involving the endpoints of the integration. In other words, if we want to integrate from A to B, then we will involve these 2 points in the actual integration. So if we talk about the integration through the thickness of the shell or through a beam element thickness, then we would have here the top and bottom surfaces involved. The bad point, or well, I shouldn't say bad, but certainly it's not a very advantageous point of the Newton-Cotes integration is that we need to involve a fairly large number of integration points or integration point stations to obtain an acceptable accuracy when we talk about finite element analysis. And therefore, the Gauss numerical integration is a more attractive scheme. And in fact, we will find that in finite element analysis, we almost always use Gauss numerical integration. There are only certain special cases in analysis of beams, plates, and shells where we in fact use the Newton-Cotes integration. And the reason then, of course, is that we want to obtain also surface stresses and strains. That would be, for example, one reason. Now, in Gauss numerical integration, the basic concept is quite similar to the concept that we just discussed, that we again use an interpolating polynomial to lay through the function over the interval a to b. The important point, however, now is that we use, if we look at our function here, here's the interval a to b, our r-axis here. If you look at that function, is that we, in Gauss numerical integration, do not use equal spaced intervals. In Newton-Cotes integration, we use equal spaced intervals and we involve the endpoints. In Gauss numerical integration, we are using points, stations, R1 to R2 and Rn, stations that can be anywhere in the interval. And Gauss has developed the optimum stations for us. In other words, what he has said at that time is, let us optimize the particular locations of the integration point stations, and in addition, let us optimize the weights alpha 1 to alpha n. In the Newton-Cotes integration, we only optimize, so to say, the alpha values. The stations were fixed because we involved, for example, in the trapezoidal rule, we involved this point and that point. In the Simpsons rule, we use the midpoint, and so on. In Gauss integration, we say, well, let us not necessarily fix those stations, but rather let us optimize the location of these stations. Well, since we then can optimize the values of the alpha 1 to alpha n, these of course are n components, and the stations R1 to Rn, which are also n components, we really can optimize 2 n components. Now, if we look at the fact that we are dealing with 2 n components that we optimize now, and the fact that the interpolating polynomial, of course, also involves one constant, then we find that the interpolating polynomial can now be of order 2n minus 1. 2n minus 1. Whereas in the Simpsons rule, the interpolating polynomial with n stations could only be of order n minus 1. You see, in the Simpsons rule, for example, with 3 stations, the n was in the Simpsons rule equal to 3, but the order of the interpolating polynomial was 2. In other words, a parabola could be integrated exactly. Now, in the Gauss integration, we are talking about an interpolating polynomial that can be of order 2n minus 1, a much higher order for n stations, Here, with the Newton-Cotes rule, for n stations, we only get an interpolating polynomial of n minus 1. Well, Gauss has developed the specific stations R1 to Rn, to be used, and the weights, in order to fit the interpolating polynomial through the actual function that we want to integrate. And of course, we also know now the error that is involved, Rn. The error, of course, being now much smaller than in the Newton-Cotes formula, because we are dealing with a higher order interpolating polynomial. The Gauss values are given here. When n is equal to 1, well, we only use the midpoint, and the alpha value is 2. When n is equal to 2, in other words, we are talking about 2-point integration, then Ri is equal to plus minus 0.577 and 1. In this particular case, we are using the fact that we want to integrate from minus 1 to plus 1. In other words, our r here is this coordinate here, and we are integrating from minus 1 to plus 1. So in 2-point integration, we are using a point here, which is minus 0.577, and another point here, which is plus 0.577. Notice that we are feeding in these points to a high order accuracy in a computer program. Typically, in a computer program that runs on a CDC machine with 14-digit precision, we would actually put these points in to 14-digit precision. Of course, they are actually they are put into the subroutine. They are there, and the computer program just picks up this value and evaluates then, of course, the function that we want to integrate at that station. The factor that the function has to be multiplied by is given here. In 3-point integration, we use 3 points. This one is the easiest to look at. It's right the center point, and then there are 2 more points, one at minus 0.77 and one at plus 0.77. In finite element analysis, we know, of course, or in isoparametric finite element analysis, I should really say, we know, of course, that our integration runs from minus 1 to plus 1. So these are the actual values to be used. And these are the actual values that you would find, for example, in a computer program such as Ardina. If we want to integrate an interval from a to b, I like to simply mention that, of course, the same scheme can directly be used. If we have the Ri and alpha I for the interval minus 1 to plus 1, then these would be the value to be used for these integration point stations if our interval is not from minus 1 to plus 1, but from a to b. And this would be the weight that would have to be used for this particular case. The Ri and alpha I, once again, are the same Ri and alpha I that I listed here in this table. Well, so far we really talked about one-dimensional integration. However, the same concept can directly be used for multiple-dimension integration. In other words, if we talk about the integration minus 1 to plus 1, for example, as we would integrate, of course, in the formulation of a truss element. If we now want to go through the integration of a 2-dimensional element, then we would have to integrate a 2-dimensional function in R and S, and that means integrating twice, once with respect to R, once with respect to S, and we can use the same concept that we use in analytical integrations, namely first we integrate with respect to R, That gives us 1 alpha I here, and then with respect to S. And the final result is shown here, that we have to bring in a weight factor alpha I and a weight factor alpha j. This one for the R integration, that one for the S integration. And of course, stations Ri and Sj are the stations at which we would evaluate the actual function. Notice one important point, that we could use a different order of integration into the two directions. For example, if we have an element such as this one, two-dimensional element, 2 nodes here through in the S direction, but say 3 nodes in the R direction, so our R axis is this one, our S axis is that one, then in this particular case, since we're using a higher order interpolation into the R direction, in this particular case we might say, well, let us use 3-point integration this way, but 2-point integration into the S-axis. So here 2-point integration into the S-axis, but 3-point integration into the R-axis. And of course, the same concept applies also in 3-dimensional analysis. In 3-dimensional analysis, as an example here, we would have the f now being a function of r, s, and t, 3 times integration from -1 to +1, and the final result just derived just the same way as in 2-dimensional analysis is given here. Notice once again, we can use different orders of integrations into the 3 directions. I should also mention at this point that when we talk about an actual stiffness matrix, of course we talk about an array n by n for a 3-dimensional element, say a 20-node brick. This would be a 60 by 60 stiffness matrix, and every one of these elements here in that stiffness matrix would be an f, such an f. Every one of these elements would be integrated as shown here. Let us now look at the practical use of numerical integration. Well, the first important point is that the order of integration that is required to evaluate a specific element matrix can, of course, be evaluated by studying the function f to be integrated. In other words, if I want to evaluate a certain stiffness matrix, K, here is the stiffness matrix given. If I want to evaluate that stiffness matrix exactly, I could look at each of these elements, and there are now many of these f functions in there. Let us look at that one. I would look at that f value and identify its dependency on r, s, and t, linear, cubic, parabolic, and so on. And then I could, by entering into, by the use of the Gauss numerical integration or the Newton-Cotes integration, and by looking up the errors involved, I could identify what integration order I need in order to evaluate this integral exactly. That can be done, and for simple elements, relatively simple elements, in other words, 4-noded elements that are squared, or 8-noded elements that are squared, we can fairly simply evaluate the order of integration that is required. However, when the element is curved, in other words, when we talk about a general element like that, the required integration order is not that easily assessed in order to evaluate the stiffness matrix exactly. And the reason for it is that we have the Jacobian transformation in there. Therefore, in practice, the integration is frequently not performed exactly, but we have to remember that the integration order must be high enough. Well, considering then the evaluation of the element matrices, we should notice the following requirements. For the stiffness matrix evaluation, we note that the element matrix should not contain any spurious zero-energy modes. What do I mean by that? Well, I mean that if I have an element such as that element here, we know that if you're talking about a plane stress element, there are only 3 rigid body modes. one translation, rigid translation this way, one rigid translation that way, and one rigid rotation of the element that way. These are the only three rigid body modes that the element stiffness matrix should contain. It should, of course, contain these in order to satisfy the convergence requirements that we discussed earlier. What I'm saying now is that my integration order should be high enough so that there is no additional zero eigenvalue. If there is an additional zero eigenvalue, I might run into serious numerical difficulties in the solution of the overall governing equilibrium equations. And I will give you just now a very simple example. The second requirement is that the element stiffness matrix should contain the required constant strain states. So basically what I'm saying here is that the numerically evaluated, numerically integrated stiffness matrix should still contain the requirements that we discussed, which the element must satisfy for convergence. For the mass matrix evaluation, here, well, we only need to satisfy that the total mass must be included. In other words, the numerical integration should pick up the actual mass of the element. If that were not the case, then the total analysis, considering the total analysis, we would have lost some mass. The fourth vector evaluation here, also the total loads must be included, must be picked up, so to say, by the numerical integration. Let us look at this requirement here, and there I have a very simple example. Here we have the 8-node element, plane stress element, which is supported here on a hinge and here on a stiff spring. I apply a load P there. If I use 2x2 Gauss integration, I get absurd results. If I use 3x3 Gauss integration, I get the correct results. The correct results, of course, being that the element simply rotates about this point A. It simply rotates about the point A as a rigid body. And of course, extending in that rotation the spring at point B. The absurd results here come about, using 2x2 integration, come about because the stiffness matrix K does not contain just 3 rigid body modes, but 4 rigid body modes with 2x2 Gauss integration. Now, 3 rigid body modes are suppressed by the hinge here and the spring there. They are suppressed. But if I look at the fact that we are now having 4 in the stiffness matrix, if I suppress 3, I still am left with 1 rigid body mode. And that means 1 zero eigenvalue. So this is still an unstable structural stiffness matrix. And when I subject that stiffness matrix to a load P, I get absurd results. Therefore, this is a very simple example that demonstrates that the Gauss integration has to be high enough in order to prevent instabilities occurring in the solution of the equations. In practice, of course, what happens frequently is that we are using these elements in a mesh. So we have an 8-node element here and another 8-node element here. And if we use 2x2 integration for this element and 2x2 integration for that element, we might very well be able to solve the equations very nicely, and we might in fact get good results in an analysis of a more complicated problem, because the stiffness of this element and that element, they each other compensate for the loss of the or for the rigid body mode that still consists or still is available in this one element here. In other words, although this one element is unstable, when we look at it numerically, when we solve the equations for a single element, as shown here, when the element is surrounded by other elements, they provide enough stiffness into this element so that the overall solution of the mesh is still, can still be obtained, and we obtain, in fact, good results. However, If you do use reduced integration, we call this reduced integration because we are not evaluating the stiffness matrix exactly. If you do use reduced integration, you should be aware of this fact that for a single element or for certain element mesh layouts, we can run into numerical difficulties. Let's look briefly at the stress calculations. Surely stresses can be calculated at any point of the element, and they would be evaluated as shown here. The stress-strain law is here. Here we have the strain displacement interpolation matrix. Here we have the nodal point displacement vector. Of course, these nodal point displacements are now known. They are now given. This is an initial stress vector, which is also given. We should notice that the stresses are in general discontinuous across element boundaries. If we look at a practical analysis, we might actually not evaluate the stresses at the boundary of an element, but we might evaluate the stresses at the integration point. So if we look at a mesh of elements as shown here, we might evaluate the stresses at the 2x2 integration points, shown here for that element. If we were to evaluate the stresses of this element at this boundary and of this element at that boundary, we would see a stress jump. I should mention here, just as a side note, that in fact one can show that the stresses at the Gauss integration points are somewhat better predicted in a finite element analysis than along the boundary of the element. So that is another reason why we use why we predict stresses rather at the Gauss integration points and not on the boundaries of the element, using directly this approach. As an example here, let us look at a very simple problem. Here we have a cantilever modeled with two 8-node elements. Now remember that these two 8-node elements each contain the parabolic displacement variation. So since this is a bending moment that we apply to that cantilever, and since this bending moment of course gives a parabolic displacement variation, the finite element solution will be correct, will be exact in this particular case, and therefore there will be no stress jump here. Since the elements contain the displacements that shall be predicted, that are the analytically correct results, the finite element mesh will predict these displacements, and of course in that case we have stress continuity. This is shown here by, we have dissected these elements here. This is element 2. This is here element 1. And we have plotted the stress distribution along the line ABC. Here's the line ABC. And as you can see, there's 900 here and there's 900 there. And of course, a linear variation stresses, so no stress jumps there. However, if we look at the same problem, the same cantilever, I should say, with now an edge shear load as shown here, then these elements cannot represent the exact displacement distribution in the cantilever because they only contain a parabolic variation in displacements. And in this case, we have the stress discontinuity. Tau xx, in other words, the stress into this direction here, the normal stress. For this element for element 2 along ABC, you can see 1744 up there. And then 0 at the neutral axis because of symmetry conditions, of course. And for element 1 along ABC, we have 1502 right there. So there is, in fact, this stress discontinuity that I was talking about earlier. The shear stresses here have also a slight discontinuity, as you can see, 291.38 to 96.48. The reason that we have the stress discontinuity here is, of course, that the elements cannot represent the exact solution, and therefore they each try to, in the integral sense of the finite element formulation, try to predict the solution accurately within its domain, and the result is that we have a stress discontinuity between elements. Finally, let us look then at some modeling considerations. In order to solve a problem we should really have a qualitative knowledge of the response to be predicted. We should also have a thorough knowledge of the principles of mechanics and the finite element procedures available. And this, of course, is the subject of my lectures here to you. If we have these two knowledges, then we should still know a little bit more about what kind of elements we should use, how one element performs versus another. And here, the first remark that I like to make is that parabolic undistorted elements are usually most effective. Here, please see that I'm saying usually most effective, because in some earlier lecture I talked about the analysis of fracture mechanics problems where we in fact distort elements to pick up stress singularities. But if we don't talk about stress singularities or special situations, usually the parabolic undistorted elements are most effective. Here I have put together in a table the kinds of elements that I would recommend for usage. These are typically also the elements that are used in general purpose code such as Arduino. Truss or cable element, the 2-node element is quite effective. In some cases we want to use a 3-node element or 4-node element, but the 2-node element is cheap and very effective in modeling. For 2-dimensional plane stress, plane strain axisymmetric analysis, the 8-node or 9-node element, those are the elements most effective. And as I just mentioned, we should use them undistorted, in other words, rectangular. The 3-dimensional analysis then, in 3-dimensional analysis we would effectively use the 20-node brick element, which is really the counterpart of the 8 or 9-node element. For the 3D beam that is curved, we would use 3-noded elements or 4-noded elements, better even 4-noded elements. Of course, if we have a straight beam, then we would use simply the engineering Hermitian 2-noded beam. But if we talk about a curved beam, then the isoparametric beam that I presented to you in lecture 7 is very effective. The plate and shell elements that I would recommend are this element here for plate analysis. I mentioned that already earlier. And for the shell analysis, the 9-noded element and the 16-node element. Even for plates, it might pay sometimes to use the 16-node element, which is very effective and particularly works for very, very thin plates and shells. It does not have the deteriorating behavior or the locking phenomenon that I referred to in lecture 7. Let us look also at some mesh considerations. If we perform an analysis, we might find that in some area of the element idealization we want to use 4-node elements or lower order elements, and in another area we want to use higher order elements. Well, here I have shown a transition region going from a 4 to a 5-node to an 8-node element. Notice that we have full compatibility along this side. So this is a compatible element transition from 4 to 8-node elements. And similarly, of course, in 3-dimensional analysis, you could go from 8-node bricks to 20-node bricks via using these such transition elements. An alternative approach would be to use a 4-node element here and say 2 4-node elements there. But notice that if you do so, the displacements at node A have to be constrained if you want to preserve compatibility here. Notice that along BC, for this 4-node element, we have a linear variation in displacements because we have only UB, VB, UC, VC there. And of course here for these two 4-noded elements we have a linear variation from here to there and another linear variation from here to there in displacements. To preserve full compatibility along this line, these two constraint equations have to be used. And that means really that VA and UA are set to the mean of UB, UC, and VB, VC as shown here. Another transition approach is shown here on the last view graph that I wanted to present to you. And here we're going from 8 node elements or 7 node elements. If you wanted to use 8 node elements here, then of course you would have to put another node in there each. So here we're going from 2 layers of 8 node elements over into 1 layer of 8 node elements. Notice that in this particular transition region here, we are using a distorted element. Of course, that means the order of accuracy that we can expect here in the stress predictions and so on is not quite as good as we would like to see it. So this transition region should be away from the area of interest, the area of interest being somewhere over here, far away from the transition region. However, we do have a compatible element layout, and that, of course, is an important point which I mentioned to you earlier, that we would like to preserve compatibility as much as possible. And for that reason, of course, we have developed these variable number node elements. This concludes what I wanted to say in this lecture. Thank you for your attention.